Hey guys, welcome back. This is going to be lecture 13 and we are going to be covering chapters 3.5 and 3.6, polynomial and rational functions and inequalities. So let's begin. First, a little introduction. We're going to have a definition of a rational function. It's saying let P and Q be polynomials where Q is non-zero. And all this means is here, it's just saying that the denominator is not 0. So then we have f of x equals p over q is a rational function. Some examples of rational functions would be like, you could have f of x equals x squared plus x minus 1 over x plus 7, right? So this would be p and this would be the q's. That's all it's saying. Okay, so the domain of a rational function is all real numbers excluding all the real zeros of q because the denominator cannot be 0. So some examples, we have f of x is equal to 1 over x. It's already factored. And then its domain is it can't be 0 because then you'd have 1 over 0, which is a sad time. So that means our intervals are going to be from negative infinity to 0, union 0 to infinity. All right. Next, we have g, which is 5x squared over 2x squared plus 5x minus 12. And then if you factor this bottom part using the AC method, you'll get 2x minus 3 times x plus 4 here on your denominator. And then if you have like 2x minus 3 can't be 0, that means 2x can't equal 3, which means x can't equal 3 over 2. Which is how they got x cannot equal 3 over 2. And then similarly how they got negative 4. So then this makes our domain and interval notation. We go from negative infinity to negative 4, and we have to stop here because negative 4 makes this denominator 0. And then we union it with negative 4 to 3 halves, but again we have to stop at 3 halves because that one makes the other piece of the denominator 0, this bit. And then we can go from 3 halves to infinity. All right, lastly, we have x plus 3 divided by x squared plus 4. With this one, you can notice that there is not a time where x squared will equal negative 4, right? Like if we have x squared plus 4 equals 0. So since a squared term cannot equal a negative number, this denominator will never be 0, okay? That means our domain is just going to be all real numbers because we don't have any restrictions. All right, so it was just definitions. So here are some rules. So if we have x is approaching c plus, this plus here means from the right. This minus means from the left. And then you have x approaches infinity and x approaches negative infinity. So what we're going to do is we're going to use these in this next example to find as x approaches negative infinity, f of x is going to approach what? So what we're going to do is we're going to take a peek of its graph. I'll draw it for you really fast over here. So the graph of 1 over x squared looks like this, where it has these kind of two pieces on the first and fourth quadrants of our plane. So this is the y-axis, this is the x-axis, right? And then this is my graph, y equals x squared. So I always like to look at the graph as the picture, and let's first look as x approaches negative infinity. So here's negative infinity, and then to the right is going to be positive infinity, right? So as x approaches negative infinity, our graph here is going to get closer and closer and closer and closer to this x-axis, right? Well, what does y equal at the x-axis? Remember that y always equals 0 when we're on the x-axis. So that means as x is approaching negative infinity, f of x is actually approaching 0. All right, let's think about what happens as x approaches 0 from the left. Remember that minus that kind of looks like an exponent means from the left. So what is f of x approaching? All right, well, let's take a look. So coming from the left means we're starting over here, right? This is the left side, this is the right side. So we're starting over here. And if you think about like a little dude and he's walking up along this line, where's this little dude going? So he'll kind of keep walking up and up. And since this arrow is going up, we'll just go up and up and up and up. So as our x's are approaching 0, so we have -4, -3, -1, -1/2, stuff like that. As we're getting closer and closer to 0, coming in from the left side, our little dude is walking higher and higher and higher and higher. And what is up this way? Well, that's infinity. So that means as x approaches 0 from the left, our y is actually approaching infinity. All right, let's do some more. So what about as x approaches 0 from the right? Where does f of x approach? So if we're coming from the right, that means we're going this way. We're coming from the right and we're going towards x equals 0, right? So I put my little dude here on my graph, and he's walking towards the x equals 0, and what he's doing is walking up and up and up and up and up, right? So as we get closer and closer to 0, our points are going to be really, really high up towards, you guessed it, infinity. So as x approaches 0 from the right side, our y value is going to go towards infinity. Do you see? All right, we've got one more to do, and that is going to be as x approaches infinity, what is happening with f of x? All right, let's check that one out too. So as x is going towards infinity, and remember infinity, positive infinity is going to be this way. As x is getting closer and closer and closer and closer to infinity, y is getting closer and closer and closer to the x-axis. So again, it's going to be kind of the same story as it was with this side. We are approaching 0, our value of our function. So as x is going to infinity, y, or f of x, is going towards 0. Do you see? Because it won't cross this x-axis. All right, and that's how you solve these problems. So when it's asking what is y doing as x is approaching, I generally like to look at the graph of the function, and then I like to think about the little dude walking on the graph as well. All right, let's keep moving on. So next we need to talk about vertical asymptotes. So vertical asymptotes are when a function is approaching a line, you could call it like x equals c, and it can never cross it. And as it gets closer and closer to that line, it gets infinitely bigger. So let's go through some examples on how to find a vertical asymptote. So how you're going to find the vertical asymptote, it's very simple. You're going to just set the denominator to 0 and then solve for x. So we'll have, for f, we'll have x minus 3 equals 0, which means x equals 3 is the vertical asymptote. In a picture, so here's x equals 3 right here, I put this dot. So our vertical asymptote is going to be this line here at x equals 3. And then our graph cannot cross it. However, as our graph gets closer to it, it will trend towards infinity. So what that would look like is it gets very close to the graph here and does this. And then on this side, all right, so here's my graph. And you see how as x approaches 3, from the left, which is this side, we are actually, as we're getting closer and closer to 3 from the left, we're trending towards negative infinity. So as x approaches negative 3 from the left, f is going towards negative infinity, right? It's going down, 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 down. However, as we approach 3 from the right, this way, we're walking, walking, walking towards the 3, all of a sudden we start climbing really quickly. So as x approaches 3 from the right, f of x is going to infinity. However, as x approaches 3 from the left, f of x is going towards negative infinity. You see? So that's what an asymptote does, is on either side of the asymptote, the function either goes from infinity or to negative infinity, or both ends could go towards infinity, kind of like this one, where both of them went towards infinity here. Or both could go to negative infinity as well. All right, let's find the vertical asymptote for number 2. All right, so we'll have 3x squared plus 5x minus 2 equals 0. And remember, when we do the AC test, we want to multiply a times c. So we'll do 3 times negative 2, which is negative 6. We want factors that are going to add to positive 5. So I think what'll do it is going to be 6 and negative 1. And this is where the factoring gets kind of tricky. Now, if you know how to factor this, you can skip ahead a little bit in the video, but I'm going to quickly explain how we're going to factor this. So we need the 3 to stick with one of the x's. So we're going to put a 3x here. The next one we'll just need an x, and we still have equals 0. And then one of our little multiplier pairs, like if you think of it as like distributing, it's the outside and the inside pairs. One of them will need to equal 6x, and one of them will need to equal negative 1x, because 6x minus 1x is 5x, which is our middle term. So we need 2 of these to multiply so we can get our middle term. See the 5x here? So that's what we're trying to figure out. So I picked this one to be the 6x one because I already have a 3, and that means this one can just be plus 2. And then this bit, this times this needs to equal negative 1x, and all I have is x, so I just need negative 1 here. And that's how you get your tuples, your 3x minus 1 and your x plus 2. All right, let's keep going. So this means that 3x minus 1 equals 0, or x plus 2 equals 0. So we have 3x equals 1, which means x is a third as one of our asymptotes. And then this is x equals negative 2. So these are our 2 asymptotes, okay? All right, let's move on. So for horizontal asymptotes, if f is a function defined by f of x equals, and then it has a lot of letters. All this is saying is we have some high power of x, and it has a coefficient. That's all this is saying. And then when we're dividing by a different power. So one of them is n, one of them is m. So first rule is if n is bigger than m, then f has no horizontal asymptote. This means since n is the degree of the numerator and m is the degree of the denominator, that means if the degree of the numerator is bigger than the degree of the denominator, we have no horizontal asymptote. An example of this would be f of x equals x cubed minus 2x plus 1 divided by x squared minus 7. So the degree in the numerator is 3, and the degree in the denominator is 2. And 3 is bigger than 2, so this has no horizontal asymptote. If n is less than m, so it's the degree in the numerator is less than the degree in the denominator, then the line y equals 0, or the x-axis, serves as the horizontal asymptote of f. For example, if you have f of x equals x minus 1 over x squared plus 4, this would have the horizontal asymptote of y equals 0. You know immediately because the degree in the numerator is 1, and the degree in the denominator is 2, and 1 is less than 2. Because this is like x to the 1, right? And it's just x, you think of it as x to the 1. Lastly, if the exponents are the same, then the line y equals a m b m is the horizontal asymptote of f. That sounds confusing, but remember, look up here. These are just the coefficients. So for example, if you had f of x equals 3x squared minus 10 divided by 5x squared plus 2, then your horizontal asymptote would just be the coefficients of the x squareds. So it's going to be y equals 3/5. Similarly, if you have f of x equals x squared minus x plus 1 divided by, let's do 2x squared plus 7, you would think of this as an imaginary 1 right here. And that means your horizontal asymptote would be y equals 1/2. Okay? All right, let's keep moving on. Okay, cool. So we get to do some examples now. So what we're going to do is figure out whether or not they all have horizontal asymptotes. So the first thing we're going to do is check the exponents. So number 1, we have that the degree in the numerator is 2. So the degree of the numerator is 2, and then the degree of the denominator is 4, and 2 is less than 4. So if we go back up here and we look, we see here degree of the numerator less than the degree of the denominator. That means y equals 0 is the horizontal asymptote. So this one was nice and straightforward. So our horizontal asymptote is y equals 0, and we are done there. All right, let's do number 2. So for number 2, the degree in the numerator is 3, which is bigger than the degree in the denominator, which is 2. And if we scroll back up, we can see if the degree in the numerator is bigger than the degree in the denominator, we don't have one. So this is pretty straightforward. So no horizontal asymptote. We are done there. All right, last one. So the degree in the numerator is 2, and the degree in the denominator is 2. So our degrees are equal. So that means our asymptote is going to be the coefficients of our x squared terms. So the coefficients are 8 divided by 2. So that means our horizontal asymptote is going to be y equals 8 divided by 2, which is 4. So y equals 4 would be your answer. Not too bad, right? Okay, let's keep moving on. So next we're going to learn about slant asymptotes, and slant asymptotes happen when the degree in the numerator is exactly 1 greater than the degree of the denominator. Exactly 1. Very important. To find an equation of a slant asymptote, divide the numerator of the function by the denominator. The quotient will be linear, and the slant asymptote will be in the form y equals quotient. So that's a lot of verbiage to really just tell you that you just need to divide. So for this choice, you can use either long division or synthetic division. It doesn't matter. I'm going to choose synthetic because in my opinion, it's just more straightforward. So for synthetic division, you need, and long division too, you need an x of every power, and we're missing an x to the 1 in our numerator. So we can actually rewrite this as x squared plus 0 times x to the 1 plus 1, since 0 times x is 0 over x minus 1. Now what you're going to do for synthetic division is you remember that the quotient is always in the form, I think it's x minus r. I think that's the letter they use. So that means we're going to pick 1 to go up in this corner. And then we want the coefficients of the numerator polynomial. So the coefficient of x squared is 1, the coefficient of x is 0, and then we just have 1, right? So then you have, you bring down the 1, and then 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, and then we end up with a 2, so it's not a factor, but we don't really care. All we're interested in this bit. So this means this is going to be x plus 1 is going to be our slant asymptote of y equals x plus 1. All right. I'm going to go ahead and show y'all how to do this with long division. If you know long division or prefer synthetic, you're welcome to skip ahead in the video. All right, so long division, you're going to do x minus 1 divided by x squared plus 0x plus 1. So looking at x minus 1, we want to figure out how we can multiply it to get x squared, right? So I know that x times x minus 1 equals x squared minus x. And I'm trying to cancel out this x squared term. So this is actually good. We want this. So that means my factor is going to be x. So x goes up here, and then we'll have x squared minus x here. So this guy that we wanted. And you're subtracting this whole thing. So when you distribute this negative, that becomes a plus. These cancel out, and you just get x plus 1. Well, now this is pretty convenient because I have an x here and an x here, which means I don't need to multiply by anything to make my first terms be the same. So I can just add 1, and that means 1 times this boy is just going to be x minus 1, and I'm subtracting him, which means this becomes a plus, this stays minus, x's cancel out, and you get a remainder of 2. So again, we got the same answer we did from synthetic division. That means my slant asymptote is going to be y equals x plus 1. And that's how you figure out how you have a slant asymptote. Let's keep moving on. All right, now we want to graph a function. The first thing that we're going to want to do is find the y-intercept. To do that, remember we just plug in 0. So we'll get 4 times 0 over 0 squared minus 4, which is 0 divided by negative 4, which is 0. So that means our y-intercept is the origin, 0, 0. The next thing we want to do is find our x-intercepts. What's really nice about the rational equations is that the denominator can never be 0. So when we're finding the x-intercepts, we really just want to focus on when the numerator is equal to 0. And we want to make sure that's not a restricted value. So 4x equals 0 just means that x equals 0. So our x-intercept is also 0, 0. So we're good there. We're only intercepting at the origin. All right, now we want to identify the vertical asymptotes. So step 3 is going to be vertical asymptotes. So that means we're going to have to find the zeros of x squared minus 4. That's going to be x squared equals 4, which means x is going to be plus or minus 2. Right, if we take the square root of both sides. So those are my vertical asymptotes. Next, we want to figure out if it has a horizontal or a slant asymptote. So this is step 4. So the degree in the numerator is 1, and the degree in the denominator is 2. So that means the degree in the numerator is less than the degree in the denominator, which means our horizontal asymptote is y equals 0 per our table. This is vertical asymptote. Per our table that we looked at earlier. Lastly, we are allowed to cross a horizontal asymptote. So what we can do is plug in the 0 and see if we cross our asymptote or not. Well, when we plug in 0, we do get 0. So we do cross our horizontal asymptote. Lastly, we want to determine the behavior of our graph. So what we're going to do, oh, I forgot to write. So what you can do is plug in points on the number line and see if f is like positive or negative and stuff like that. So here we have, we're going to plug in x is -2, x is 0, and x is 2, since these are our vertical asymptotes, and this is our horizontal asymptote where we cross it. So what I'm going to do first is plug in, let's do like -3. So f of -3 is going to equal 4 times -3 over -3 squared minus 4, which is equal to -12 over 9 minus 4, which is equal to -12 over 5. So that means it is going to be negative on this interval. Negative. This is a negative infinity, and this is to infinity also. All right, next I need to pick a number between here and here. So I'm going to pick -1. So I'll have f at -1 is equal to 4 times -1 divided by -1 squared minus 4. There's going to be -4 over 1 minus 4, which is -4 over -3, which that cancels out and we get a positive 4/3. So that means this interval, my f is going to be positive. All right, next, this interval. So I'm going to plug in 1 in this interval. So f at 1 is going to be 4 times 1 over 1 minus 4. This is 1 over -3. I'm sorry, 4 over -3. So this is going to be negative. And then I'm going to plug in one more point. I'm going to find what happens at f of 3. So it's going to be 4 times 3 over 3 squared minus 4, which is 12 over 9 minus 4, which is 12 over 5. So this is positive number. So that means it's going to be positive here. All right, now since I've kind of run out of room, I'm going to erase all of this scratch work right here. So, you know, hit pause or take a second if you need to copy this down, but I'm going to erase it so I can graph our graph. All right, now that I've drawn my axes, I'm going to draw my asymptotes in first. So I know that I have vertical ones at x equals plus or minus 2. So here's positive 2 here. And then -2 is over on this side. And then I also know my horizontal asymptote here is y equals 0, which is this line. The last step is going to be to plot the points and followed by graph the function. So when we were on the interval from -infinity to 3, our behavior was negative, right up here. Looking up here. So that means I'm going to be below the x-axis, like this. All right, I then know that I crossed my horizontal axis at 0, 0, so I know that's the point on the graph. I know that I am positive from -2 to 0, so that means I'm up here approaching this vertical asymptote to infinity. And then once I cross 0, which is here, I turn into a negative graph. So it's going to be down this way. Lastly, from 3 to infinity, I am positive. So that means I am above the x-axis. So here is what my graph looks like, final answer, okay? All right, now we're gonna move on to solving quadratic inequalities. So our first example is to solve this given equality where we have 3x times x minus 1 times 10 minus, or I'm sorry, greater than 10 minus 2x. So step 1 is going to be to distribute this 3. So we'll have 3x squared minus 3x is greater than 10 minus 2x. And then the next step is to get it in the form, essentially f of x is bigger than 0. This is our goal. So we are going to add 2x to both sides. That means we get 3x squared minus x is greater than 10. And then we will subtract 10 to get 0. So we have 3x squared minus x minus 10 is bigger than 0. What we'll do next is factor. So remember, we'll do the AC method. 3 times negative 10 is negative 30, and we want factors that add to negative 1. I think negative 6 and 5 will do fabulously. So we'll have 3x, and we'll have x bigger than 0. So then let's see, we want a minus 2 here. That way I have 3x minus 2x is negative 6x. Then I'll have a plus 5 here. That way I get my 5x back as well. Alrighty. The next thing that we are going to need to do is actually solve for when both of these are equal to 0. So you want to figure out, when does 3x plus 5 equal 0, right? Well, that means 3x is going to equal negative 5, which means x is going to equal negative 5/3. Similarly, when x minus 2 equals 0, that means x equals 2. Now I have this number line here. And I'll have negative 5/3 and 2. All right. And what I basically want to do is figure out where my function is bigger than 0. Which interval? Is it negative infinity to 5/3? Is it negative 5/3 to 2? Or 2 to infinity? Where is my function going to be bigger than 0? Okay, that's the goal. So what we're going to do is test values. For negative 5/3, I'm going to use negative 2 because that's smaller than negative 5/3. So negative 2 lives somewhere around here. So we want to find f of negative 2. All right, let's figure it out. So that means we'll have 3 times negative 2 squared minus negative 2 minus 10, which is equal to 3 times 4 plus 4 minus 10, which is equal to 12. Let's see, 4 minus 10 is negative 6. So this equals 6. So we have f of negative 2 equals 6. Next, we want a number between negative 5/3 and 2. I'm going to pick 0 because that's going to be nice and easy to plug in. So f at 0. So we'll have 3 times 0 squared minus 0 minus 10. That's 3 times 0 minus 10, which is just negative 10. So negative 10. So far I've got positive here, negative here. Now I want to figure out my third interval. I'm going to plug in 3 because it's bigger than 2. So I'll have 3 times 3 squared minus 3 minus 10. This is going to be 3 times 9 minus 13. 3 times 9 is 27. And 27 minus 13 is 14. So that means f of 3 equals 14. So this is positive. So where my set is bigger than 0, I'm sorry, not set, where my function is bigger than 0, my answer is going to be from negative infinity to negative 5/3 not including 5/3 because it's not greater than or equal to, right? It's just greater than, union 2 to infinity. So I like to call these little number line things we're making, I like to call them sign charts. So basically you make your sign chart and you plug in values in between the borderline number and, you know, either infinity, negative infinity, or each other. You kind of try to find numbers in between that aren't too bad to plug into your formula. Oh, this is 3, I forgot to write it. And then you just see if your solution is positive or negative. And that's pretty much it. And since we wanted bigger than 0, right here it says bigger than 0. That means we only wanted the bits where it was positive. So we don't want that bit because it's negative. We're going to move on to solving rational inequalities. So the first thing that we want to do is have it less than or equal to 0. So we want to get this 3 over here on the other side. We do that by subtracting it. So that means we'll have 4x minus 5 over x minus 2 minus 3 is less than or equal to 0. And then we want to be able to make this into one fraction. So we'll have minus 3 times x minus 2 over x minus 2. And then we'll have, let's see, 4x minus 5 minus 3 times x minus 2 all over x minus 2 is less than or equal to 0. Next, we'll combine like terms. All right, once we're here, remember that the denominator can never be 0. So what we want to do is figure out when the numerator is going to be 0. So it's going to be x plus 1 equals 0, means x is negative 1. Then we want to find our boundary point, which is when the denominator is equal to 0, because we can't have that. So that means x is 2. So now we're going to make our sign chart. We have negative 1 and 2. All right, so for the interval negative infinity to negative 1, I'm going to choose negative 2. So that means we'll have f of negative 2 equals something. So I have negative 2 plus 1 over negative 2 minus 2, which is equal to negative 1 over negative 4, which is overall going to be positive. So it's going to be 1/4, and it'll have positive value. Next, my favorite number between negative 1 and 2 is, of course, going to be 0. So that means I'll have 0 plus 1 over 0 minus 2, which is just 1 over negative 2, or negative 1/2. That's overall negative. All right, lastly, I'm going to plug in something bigger than 2, so I'm going to pick 3. Oh, this was 0, sorry. So f at 3 is equal to something. So that means we'll have 3 plus 1 over 3 minus 2. This is going to be 4 over 1. So we get f of 3 is equal to 4, which means this one is overall positive. However, this time we were interested in the spots where it was less than or equal to 0. So it's actually going to be my middle section here. We want this one. Now, here's where it gets tiny bit tricky. We can't have 2 because it's a boundary point, right? If we included 2 in our set, that means we're allowing the denominator to equal 0, and we can't do that. So that means our solution is going to be close bracket negative 1, because we do want to include the option for it to be negative 1. That just means the numerator is 0, comma, 2, into parentheses. And it's an open parentheses because we're not including that 2. And that's it. Thank y'all again for tuning into these lectures. I hope y'all have a wonderful rest of your day.